Alright, now let us move to the next part where we will be building the vector store for our pipeline. Okay, we have seen what is happening in chunker, which is creating the text chunk objects. We have seen in embedder what it creates as embedded chunk objects, and now those embedded chunks will be stored somewhere, and that will be stored in your vector store. Now if you can recall from the architecture diagram, we are using Cloud SQL, and Cloud SQL service acts as a relational database as well as a vector database. It uses PG vector. So embedded chunks, okay, are going to be stored in the Cloud SQL's chunks table. We will be inserting all our chunks there in that table, which provides us the semantic search functionality. Okay, and if you know, this is the heart of the entire system. So every agent query flows through this particular file, obviously, right? So when the missing results agents ask, find the studies where the sponsor never posted the results, this is the file that is going to file the answer. Okay, now how does the semantic search work here? Okay, for example, the agent's questions get converted into 1536. Now if you can recall, we have the dimensions of 1536, right? Because we had a hard limit of 2000 dimensions as per the HNSW index. So that is the reason we're going with 1536, which we have already defined in embed.py. And this file then sends those 1536 dimensions to Cloud SQL. Okay, now PG vector compares them against every chunks 1536 numbers, and these chunks whose numbers are the closest, okay, meaning the cosine similarity, you'll be getting them. Okay, what is cosine similarity? You can just read up here. And now why are we using async PGS and not preferring SQL Alchemy? Now SQL Alchemy is great for standard queries, okay, but we are using PG vector, okay, in our relational DB. Vector type is not natively supported by SQL Alchemy's ORM. Okay, and async PG is the raw async PostgreSQL driver, and it gives us complete control over the SQL that we write, and that is the reason we are going with async PG. Okay, cool. All right, if you see here, async PG doesn't know what a vector type is by default, but the PostgreSQL knows. Okay, async PG needs to be taught how to convert this between Python lists and PostgreSQL columns. Okay, so let us do that. Okay, we are not going to run this file. If you see here, we're going to create this vector store object. Okay, we're going to initialize it, we're going to apply it on the embedded chunks, all of that. Okay, now here what I've done is I've already written piece of code. I'll just give you a simple walkthrough. Okay, we're going to start with importing JSON. We're going to import any, then from embedder file, which is processing.embedder, we're going to import the embedded chunks. Okay, this is where we are going to import the settings. We are going to set certain configurations. Okay, if you see, it says pool minimum size equals to 2. What does this mean? This is the minimum number of database connections to keep open at all times. You can think of connection pool like a team of workers. We at least keep 2 ready to handle the requests immediately. So if one goes down, the other one is there to handle the requests. Basically 2 database connections we are creating. After that, what is the pool max size we are setting up? It's 10. Basically maximum number of connections allowed at one single time. If we are having more connections, there is going to be more parallelism, which is great, but the memory usage that gets consumed at the DB level is very, very high. So we're going to keep it as 10, which is kind of a safe ceiling for this particular cloud instance that we'll be using. We are going to be using DBF1 micro instance. Okay, top K default 5, which is default number of chunks. Now when I put in a query, which are the basically top K, right? Which are the how many similar chunks should I be retrieving? So it's basically I'm setting it to 5. Okay, start with creating the vector store class. What does this particular class do? It is going to save my embedded chunks to Cloud SQL and enable the semantic search using PG vectors cosine similarity operator. Okay, this is broadly the life cycle that is going to follow. Okay, I'm going to create a connection pool. If you see here, just creating a simple initialization. I'm just going to create a connection pool, okay, which is our basically team of database workers. Okay, it is going to be initialized, like it is going to start as none, and it is going to be created when this init is called. Okay, we never create the connections one by one, we always use the pool connections. So this is nothing but the connection that we are creating. Okay, what is pool? We have already defined here. These are not, pool is nothing but the number of connections or the connections that we make to the database. So this is where we are making connection to the database, as simple as that. Okay, we start with defining async context manager support. Okay, if you see here, we're going to allow vector store with async with pattern. Okay, and then this is basically entry and exit into the vector store. Okay, now this is going to help us open the connection pool. This is going to help us close the connection pool. Basically this is you enter the database, you exit the database, or you close the database, as simple as that. Now let us initialize this connection pool. Okay, now what does this async function do? It creates the async pg connection pool and registers the pg vector codec, so Python can read and write from the vector columns. Okay, basically this is the read write function that we are building. Okay, now once we have created this function, we log it. Okay, we just get the information that we are connecting to Cloud SQL. For that Cloud SQL, we get the host name and the DB name. Okay, as soon as we do that, now we're going to get the Cloud SQL's IP address from .env. In .env, we have already defined Cloud SQL's env address. Okay, now if you see here, we're going to create the pool, create the connection, and we're going to get the DB host, whatever host details. Okay, if you see here, settings.db host. Yeah, once we get that, which is the IP address, okay, we are good to go. Typically we also whitelist that IP address. Yeah, which port number we're going to use? We're going to use 5432, which is a standard relational or PostgreSQL port. Yeah, so we cast it to integer because settings.db port is stored as string. Obviously we know this, right? You can just check it. Yeah, then we also take the database name, which is the clinical trial db that we have created. Okay, you can check this in .env if you want. So if I just go to .env, you can see all the details here. You can see the db name is this, user is this, password is this, all of that. Okay, so then I'm going to get the username, then I'm going to get the password. Yeah, then what is the minimum size and maximum size? 2 and 10, right? Which is nothing but the connections that I'm going to do. So maximum number of 10 connections, minimum number of 2 connections. Okay, and this init connection, this is nothing but the key parameter that is explained in detail below. Here init means run this function on every new connection. Okay, and the pool every connection the pool is going to create. So we used to register it to the pg vector codec. Let's log it. Okay, so here basically this is where we are going to connect our entire pipeline to the Cloud SQL database. Okay, and now let us just create the next async function which runs automatically on every database connection. Okay, if you see here, we are basically building this function init for connection. That is what we are building here. We're keeping it asynchronous in nature. Okay, what does it take into consideration? It takes the connection details. Okay, so if you see, this is where we register the pg vector codec. Okay, which is the translator that teaches async pg, async pg, how to convert between Python lists and PostgreSQL vector columns. Okay, without this, if you are not using this connection like this async function, okay, saving a chunk is going to give us a type error because it cannot convert a list to a vector, and reading a chunk, okay, it is going to give us this particular error. So we cannot save and read. Yeah, but with this, what will happen? A Python list can be converted into a 1536 dimension list. Okay, and this conversion is going to happen autonomously. What is connection? It's nothing but the fresh async pg connection which is just created by the pool. Okay, so this is where, if you see here, we are going to create the connection. If you see set type codec, the PostgreSQL type we are teaching async pg about, and this matches the vector type column in the chunks table. Now what we are doing, guys, don't really worry about it. We are just doing conversion. Okay, that's all. Yeah. Now here we are going to use encoder, which kind of is used for Python to PostgreSQL kind of conversion. Now when we save a chunk, async pg needs to convert our Python list into something that a PostgreSQL understands, and that is what encoder will help us do. Okay, now here if you see, we are using JSON dumps. Okay, JSON dumps, and we are passing a list. Okay, you can see here, that is how it's getting converted. PostgreSQL's pg vector accepts this JSON string format. Okay. All right. Once this encoder is created, then we have decoder. Decoder, which means PostgreSQL conversion back to Python. Now what we are doing is we are converting Python we are converting Python to PostgreSQL kind of data. PostgreSQL understandable, we are converting into Python understandable data. Okay. So once we read the chunk back, now PG vector returns that vector as a string, and JSON.load converts it back into a Python list. If you see here, we're converting it back into a Python list. Okay, as simple as that. So encoder, Python list gets converted into a vector list. Decoder, vector list gets converted back into a Python readable list. Schema is public. Okay, so which PostgreSQL schema contains the vector type? Okay, public is the default schema where our tables live. Format is text. Okay, we're going to be using text format for conversion. Okay, now we close the connection pool. If you see here, this is where we are going to just, once we have like converted our list to vector db and list to vectors and vectors to list, we're just going to connect close back the connection pool. Okay, then we're going to save those embedded chunks. Now this is very self-explanatory. Okay, we have embedded chunks. Now we're just going to save those embedded chunks into the Cloud SQL table. Okay, what does it take? If you see, it takes the list of embedded chunks and give us an integer output, which is what the number of chunks that are successfully saved. Okay, yeah. So now here we are creating an async with function, or rather an async with not function, a module. If you see, it says self.pool acquire as connection. Now here acquire checks out one connection from the pool. Okay, when this block exists, the connection is returned to the pool automatically, not closed, just returned. That's all. Okay, we're just going to iterate over the chunks. Okay, and then I'm just going to say connection.execute, and then into the chunks table, what do I want to insert? Now this is a standard PostgreSQL code, right, that we usually write. These are the fields that will be there in the chunks table, which means my Cloud SQL database will be having a table called as chunks, which will be having these columns or fields: entity ID, chunk text, embedding, chunk index, and source. So you can imagine a table with these column headers. And as of now, at the value level, I'm just placing some parameter placeholders. Okay, and these placeholders will be filled by async pg. Okay, and this is what we call as a parameterized query, which prevents SQL injection attacks, because the values are never inserted directly into SQL string, they're passed separately. Okay, and when we have also passed something called as on conflict do nothing, which means if a chunk with a chunk ID already exists, okay, then skip it silently instead of raising an error. I'm just passing all the table. If you see, this is the table name dot column name, which is a standard SQL SQL capability or writing style, whatever. Yeah, placeholders. Okay, and every single time a new record gets added, the save count gets updated to 1. We're just going to log it. Okay, if there's an exception, we're going to log it, and finally we're just going to log as to how many chunks are saved, saved count, how many chunks, all of that. Okay, then we are going to save one study record to the studies table. If you see, we are creating an async function called save study, which takes the study data, which is dictionary in nature. So this is a dictionary that contains all the study fields to save, and this comes from the parse_study.model dump that we have created. What does this do? It saves one study record into the studies table. Yeah, that is what it is doing. Okay, now what we're doing is we're just passing the data. That's all. Okay, so what does it do? It saves one study record into the studies table. Okay, it uses insert and on conflict entity ID do update, so that if the study already exists, its fields get refreshed. Now it is a bit, as I said, it is this writing style of vector store might be a bit confusing for you, but slowly and steadily you will get acquired, or you will get comfortable working with this kind of situation. Yeah, I'm creating an async with pool acquire as connection. Okay, and then I'm just executing it into the studies table. These are the column headers that I want to populate. Okay, these are the placeholders, and this is the on conflict thing that I'm setting up. Now here I'm saying on conflict with entity ID do update set. Okay, if you see, this looks a bit weird. What does this even mean? It means that if this entity ID already exists in the table, updates all its fields with the new values, all its fields with the new values. Okay, excluded dot field refers to the value we try to insert. Okay. And this pattern is called as absurd pattern. If you're coming from SQL background, you'll understand this. Now from this dictionary, we are just getting the individual records. From this dictionary, I'm getting the conditions. If nothing, then empty. I'm getting the secondary outcomes, all of that. Okay. Then I'm going to create a function which is typically used for semantic search. I'm going to create an async function called search. It takes at an argument level, it takes the query embedding, takes the top k parameters, takes the source filter, takes the NCD ID filter, all of that. This is again optional in nature. What does it give me in the output? It gives me a list of dictionaries. Okay, what does it do? It finds the most semantically similar chunks to a query embedding. Okay, it uses PG vector's cosine distance operator, okay, to compare the query embedding. Yeah, and this is a very straightforward function, okay, that we'll be using. Okay, now yeah, so at an argument level, what does it take? It takes the query embedding, which is the search query, as 1536. It takes the top k, which is how many results to return. It takes the source filter and takes the NCD ID filter. What does it return? It returns a list of dictionary. And what does that contain? It contains the NCD ID, which means which study this chunk belongs to, chunk index, chunk text, source, and the distance. Okay, build the query dynamically. You can see the base query allows, or it always uses the cosine distance. Okay, here we add the where clause only if filters were provided. As of now, the conditions I'm keeping it as an empty list, which is a list of SQL of where conditions to add the filters. Okay. Then there is an empty list of, there is a list of parameters, which is nothing but the query embeddings. Okay, parameter count to 1. Now in case if there's a source filter, you increase the parameter count and you append those to the conditions list. Okay, and then similarly for NCD ID filter, okay, you put in a where clause, increase the parameter count. Okay, top k is always the last parameter, and then I'm just putting a standard query, just a check query. Okay, select NCD ID, chunk text, chunks, index, source, embedding from chunks, where clause. Here this is where the condition goes in. Now if you see the condition that we have put here, this is where the condition goes in. Okay, and order by distance into ascending, and then I'm just going to give the limit as to what is the parameter count. Okay, yeah, and yeah. So now here we are using connection.fetch. What does it fetch? Now connection.fetch runs the query and returns all the matching rows. Okay. Here we are using star params. Star params unpacks our list into separate arguments. Okay. For example, something like this. Okay, which means at the first placeholder there's embedding, second placeholder there's study, third placeholder there is a number of top k values. Okay. We log it. So finally we get that the semantic research, search is complete, how many results we found, what are the top k parameters, all of that. And at the end, we also get to understand how many chunks are stored. Okay, now this is very, again, as I said, very self-explanatory. Okay, final here, yeah, how many chunks are stored. Okay, this is again async function. This just helps you get, if you see, we are using connection.fetchval. Okay, fetchval returns a single value. Okay, that's all. It is just going to give you how many total chunks are stored in the database. Okay, and then just a simple function to check if the study already exists, or the the chunks of that study are already saved in the database or not. Okay, so select the count from chunks where NCT ID equals to 1. Okay, so again, as I said, it's very self-explanatory. Yeah, and what does this function do? What does it return? Rather, it is going to return you true if the study already has chunks in the database, so you don't end up re-chunking the research study, and it is going to be false if it has not been processed yet. Okay, so that is your vector store. Now let's move to the next part, which is where we run the entire processing pipeline, which is where we run the chunker, embedder, and vector store, all of it together. Yeah, let's move to the next part.